course, now we will go to game theory. Last week we talked about graph theory. We have people on social networks. And the main thing is you combine mathematics with sociology. And you use mathematics to figure out things. But it's only about people on networks, okay? We have social affiliation, strong, weak links, positive, negative, so you have balance and triadic closure and all that stuff. This week we go to the next step, when the people on the social network will interact with each other. And the games are how people interact. These games can be games like you know games, but it can be any kind of interaction. And we'll see many different kinds of games. And it's formalized, so you can figure out exactly what happens. We're going to do two parts. First, we start with simple games. We have two players, and they each make a decision. And there's different possibilities. And we assume the players are rational. They want to maximize their benefit. And then we'll see all kinds of things. Dominant strategy, Nash Equilibrium. There's a famous mathematician called John Nash. There was a movie made about him and won Nobel Prize. And partly because of this. We'll see different kinds of games, mixed strategies, randomness, penalty kick in football. When you're protecting the goalkeeper, will randomly dive to the left or the right with a certain percentage. What is the percentage? We're going to figure it out. Okay, so that's the first part. The second part is we go farther to more realistic things. One thing is that the benefit is for whole society, not just individuals. And the other one is where we have sequence of moves. So this problem will be set next week. Okay. So here on the board you can see an overview of what we're going to see with lots of examples. So let's start with basic games. I want to give you the intuition. Maybe you have not seen any game theory before. Normally this is the first time. So I want to give you the intuition. And the simplest way is dominant strategies. I'll explain Prisoner's Dilemma. This is a very famous game. Best response, dominant strategy. Then sometimes you don't have dominant strategy. Then you can do what's called Nash Equilibrium. So I'll explain that. Sometimes you need that. And I'll show different games. Coordination games, anti-coordination games, like enemy, friends and enemy. And finally, sometimes you need to do like randomizing things. This is called mixed strategies. And I'll do a simple game called matching pennies. And then a principle, how to figure it out. It's called indifference. You try to define your strategy so that the other person cannot take advantage of you in some way. Then I'll show two examples from football. Run pass is from American football, and penalty kick is from soccer. It's from the rest of the world's football. Okay, so that's basically what we're going to see today. It's chapter 6 in the book, and the book gives lots of good explanations, so I really recommend looking at the book if you want to really understand things. Okay, so social network interactions. So previously the people were just friends and we didn't really, they just do their stuff. We have triadic closure, strength, affiliation, why they become friends. But they don't really interact. In the real world, people interact. And game theory is the first step to understand that. And people will make decisions and try to get some kind of benefit, something good for them, and they will try to figure out how the other person will decide. So game theory studies that, how players' decisions affect each other. And the participants are part of a game. So a game is like a well-defined interaction, so there's rules there. And there's something called rational behavior. This basically means that the players try to get the best for them, okay? That's what we call rational. But rational, we'll see, is not so simple idea. So we'll see more discussion on rational behavior later on. Okay? So we're going to see then two parts. So the first part, which is today, and then we'll continue game theory next week. This is the simple case. Two players, each one making decision, and then you see what they get. Okay? Two opposing players make simultaneous decision. This is called rational games. The word rational is actually weird because sometimes it doesn't really look rational, but it's rational in some formal way. Okay. There's something called a payoff table, and each player can figure out the best strategy. After that, we see extensions. And so here the rational play is selfish. Each player figures out what's best for them. But you can also change the rules so it's good for everybody. So the overall benefit is up. And that's something else. That's a different kind of game. That's called Pareto optimality or social optimality. And then there's also games played over time. Here we only have two. It's very simple. Each player makes one decision. Boom. But in the real world, you have maybe many decisions in order, dynamic game, sequence of moves. Not like when you play chess. So we'll see some of that also. But that's the extended part. So we start with simple games. Games with two rational players. So there's two people sitting across each other, Joe Biden and Vladimir Putin, and they're playing a game. Okay? This is a game we've seen for a long time. And the rules are simple. So in real world, of course, the rules are not always simple, but you can usually abstract away. So we'll show many games, and we'll show what's called a strategy. A strategy is like how the player should play. What is the best way to play? The best, we can show dominant strategy. Sometimes there's one move that's always the best. Sometimes not. So we'll look at the best response. Dominant strategy, if it's always best. Okay? Sometimes there's no best move. Well, then what do you do? Well, then there's something called a Nash Equilibrium. Somehow each player thinks about what the other player does, and they each have the best response to the others, and the other has the best response to me. That's called Nash Equilibrium. It's a little bit more complicated. And finally, we'll see things, many examples. Coordination games, so the goal is to work together, or anti-coordination, when they're like enemies. Okay? And sometimes people have to randomize. There's no simple strategy. You have to pick some random number. Okay? So that's kind of what we're going to see. Let me start by showing again the little game we saw in the first lecture. Okay? This is where you and the partner are studying for an exam or a presentation. So you're working together as a partner. And tomorrow there's a joint presentation, both together, and an individual exam. And if you both study, if you study for the exam, you get 92% on the exam. But if you don't, you only get 80. If both prepare for the presentation, they both get 100%. But if only one prepares, you only get 92%. And if nobody prepares, they get 84. So with these rules, you can actually figure out what is the payoff. So you have to understand how to read these tables. We're going to see lots of these tables. So if the partner decides to study for the presentation, and I study for the exam, then I will get 92 on the exam, and the partner will get 86. Okay? So if the partner decides to study for the presentation, then I have two possibilities: presentation or exam. I get either 90 or 92. So clearly I will pick the best one. That's the rationality. So I study. But if the partner decides to study, then if I do the presentation, I get 86. If I study, I get 88. So again, my best decision is to study. So in all cases, my best decision is to study. Okay? And the same reasoning can be done for the partner, because this is symmetric. So both will study if they're rational. And they will both get 88. And then the problem is, well, if they both would do the presentation, they would get more, huh? They would get 90. So being rational, trying to maximize their little benefit, actually gives them worse results. Okay? That's one of the things we're going to look at. Simple reasoning shows that each partner's strategy should be to study. Okay? But if they both prepare for the presentation, they would get more points. So what's going on here? So it's like the rationality for each individual is not the same as the global rationality. Okay? So that's just a little refresher. Before giving many examples, I want to make some definitions. Okay? We have to be very precise. We're going to use some terminology throughout the whole discussion of game theory. And we have to be exactly precise what we talk about, because we're going to do mathematical reasoning, otherwise it's very vague. So a game is the following. There's a set of participants called the players. So we will have two players. Each player has a set of possible choices or options. Rock, paper, scissors. The choice can be rock, paper, or scissors. So there's three choices, okay? So that's an example of a game, rock, paper, scissors. And the choices are called strategies. And we're not going to call them moves, huh? You could call them moves if you want them. For each choice of strategies, that means the two players each choose a move, rock and scissors, okay? Then there's a payoff. That means each player gets something or loses something. Okay, the rock will win over the scissors. So the rock choice will win. But if the other player picked paper, they will win. Okay, so there's a payoff that depends on both choices. Payoffs, usually they're going to be numbers, and usually each player prefers larger payoffs. Okay? Two players, they play once. So this is the simple case. There's only one move. If you have a sequence, then it gets more complicated. They will simultaneously, independently choose. So they don't know what the other person will choose. So it's like rock, paper, scissors. That's a real example of a game like this. So you can say they're like one-shot games. There's only one move, simultaneous. It's the simplest case. Of course, in real world, usually there's many sequences. But you have to start with the simple case first. Okay? And then we will extend it if you have sequentially doing more than one move. That's called dynamic games. Okay? So that's the basic idea. Before I start giving you many examples, we have to make assumptions, because we're going to do reasoning here. The assumptions are very carefully chosen. If you change the assumptions, things will change. So the first assumption is that the only thing that the player cares about is the payoff. There's nothing else. All the benefit is in this one number. So a player cannot be altruistic, try to help the other guy. The player only cares about the payoff. Okay? If you want to be altruistic, somehow you have to put that in the payoff in some way. Okay? Assumption 2, every player knows the full game. There's no mysteries. Every player knows everything about the game. All the rules, all the numbers in the payoff matrix, it's all known. So this is common knowledge. And each player knows that the other player knows, okay? The game is not hidden. Each player knows that the other player knows the game. Everything is open. This is called common knowledge. They know the game. They know that each of them knows the game. They also know that each of them knows that each of them knows the game, and so on. Okay, so there's nothing hidden. This is a reasonable and normal assumption. Okay, a chess also has this. Rock, paper, scissors has this too. Of course, you have You have games where the rules are hidden, where people don't know, even where the players are hidden. You don't know who your adversary is. When you are, will not talk about that. That's called games with incomplete information. That's another theory. Okay? You see, there's a lot of different theories here. Huh? So we're only going to look at the first piece of this. Okay? And the third assumption is that each player will maximize their payoff. Okay? And given a belief about the strategy used by the other players. The player will imagine what the other player will do and will try to maximize their payoff in general. Okay? This is called rationality. This is what being rational is. Okay? So the player wants to maximize. You assume players don't make mistakes. In real-world games, sometimes players make mistakes, and then in chess, champions, even Magnus Carlsen sometimes makes mistakes. Okay, it's very rare though, but he sometimes does, and so we won't consider that. Okay, the players don't make mistakes. Okay, so that's all very clear. Okay, so now what about our little exam or presentation game? This one, You have the slide from before, this one, Okay, what is your best strategy? I explained it, Actually, I showed it, If you know the other person studies, you get 88 by studying, 86 by preparing for the presentation, so you should study. But if you think the other person does presentation, you would get 92 by studying and 90 by preparing. So in both cases, you should study. That means no matter what the other player does, no matter what the strategy of the other player, you always have the same strategy. This is called a strictly dominant strategy. It's kind of the easy case, when there's one move that's always the best, basically. Okay? Study in all cases. So it's very simple in this case. Of course, if they would both prepare, they get 90. But the strictly dominant strategy is a result of rationality. It's each player like being selfishly maximizing their own little benefit. If they would talk to each other and somehow coordinate, then they can do better, if they don't cheat. Because they could always try to cheat to do even a little more, but then if the other person thinks that the first person will cheat, then we're back to this, then they're selfish again. Okay, so we'll talk about that later. But if they're both rational, like selfish, then they will get 88, each of them. And this is called strictly dominant, because they always have the best move. Okay? Okay, so let's talk a little bit about rationality before I start jumping into many games. Okay, the 90-90, which is the overall best, you cannot get it by rational, by being selfishly rational, okay? Because someone could always cheat. Let's say you do prepare the presentation, you try to get for the 90. If your partner knew this, they could still study and get 92, okay? Somehow, even if you try to be nice and do the presentation, the other person would even do better by cheating, okay? So you have to worry about cheating, okay? Okay? If you hear the payoffs reflect everything, if you want to take care about your payoff partner's grade, it has to be in the payoff. It's not here. So once the assumptions are fixed, you can't change anything. You follow rationality and the result is fixed. Okay? So basically that's how rationality works. So we start by each person maximizing their own benefit. That's real life, By default, I'm all by myself. If I want to coordinate with people, I have to do more work. So the default thing is everyone is trying to maximize their benefit by themselves. Okay? Okay, now let's start looking at some examples here. So let me talk now first about the easy case. So easy case is when you always have a best move, which is a strictly dominant strategy. So here's a game, a famous one actually. This one is called Prisoner's Dilemma. And if you have any kind of interest in recreational mathematics, whatever, maybe you heard already of this game. It's very famous, okay? So you have two suspects, criminal suspects, being interrogated by the police, okay? Separately, in independent rooms. The police is yelling at them in the two separate rooms, okay? Now, they can be charged, it depends on what crime they're charged with, they could get a 1-year sentence or more, depending on whether they confess to do the crime or not. So the policeman is yelling, did you steal the jewels of Marie Antoinette or whatever, And they say, yes, that's me, I'm guilty. Or they say, no, what are you talking about? You moron, I didn't do anything. I'm an upstanding citizen, okay? But they do independent. So here's the payoff. If one suspect confesses, I'm the guilty one, and the other does not, Okay, so prisoner's dilemma. So everything's running now. No more technical problems. If you are suspect one, you confess or not. Well, you can figure it out from here. But let me write it down here so we can see it. So this table is very important. So 0, minus 10, minus 10, 0. So this is confess, not confess. This is not confess, confess. This is number 1, this is number 2. So we can reason about this. Okay? So now we'll try to figure out what to do. What should the suspects do? Well, if suspect 2 confesses, then suspect 1 has a choice. Not confess or confess. So the best, so you look at this part of the graph. This is the first part of this couple pair here is suspect 1's payoff. So you have to pick the highest number, so that's minus 4. Only 4 years in prison, not 10. So confess. But if suspect 2 does not confess, then you also do the similar kind of reasoning. You then also look at this column. Okay? 0 is bigger than minus 1, so again, you confess. So suspect 1 always confesses, and suspect 2 always also confesses. It's symmetric. So the best strategy is always confessing. We say confessing is a strictly dominant strategy. Okay? But if both of them would be silent, they would get less. Okay? They confess, each one says, yeah, it's partly me and partly him, the other guy. You get minus 4. But if you're silent, they have no proof. Okay, so you only get minus 1. Confessing is strictly dominant. It's always the best choice. Okay? So that's rationality. Rationality means that you pick the highest number always up. They both get 4 years in prison, 4 years. But if they would have stayed silent, the police would have no proof and they would only have 1 year. But that's not, from rationality, that's not good for them. Okay? So what does that mean? That rationality does not give the best solution. In fact, this is a famous problem. This was starting from the 1950s, game theory. It was invented in the 1950s, Morgan, Stern, and von Neumann. The same von Neumann who did von Neumann computers was also doing this stuff, okay? And of course, the military, the Cold War, they loved this because you can compute strategies. So the prisoner's lemma says, how do you establish collaboration when you have individual self-interest. When each player is being selfish, how do you do collaboration? It's hard, because just doing locally the best, you don't collaborate. Okay? So this happens a lot in the real world, it seems. Okay? And for example, arms races. Arms races. So one side makes atom bombs, and the other side says, whoops, I'm behind, I have to make atom bombs too. So they both have atom bombs. Then the first side says, whoops, I have to get ahead. So they make hydrogen bombs. Then the other side says, I also need hydrogen bombs. So they go up. And in fact, it's worse for them, because it's very dangerous, all these bombs. It's also very expensive, making all these bombs, but it makes a very tense situation. So the rational decision of trying to do better than the other person or the other country is actually very bad. If they would both discuss and make like an arms treaty, they could both reduce the number of atom bombs, and they would not be in a worse position militarily, but they would have much less tension, and the world would have more peace. Okay? So this is exactly like the prisoner's dilemma. Okay? And in fact, we see that it does happen. There have been treaties. In the good old days, it was between the United States and the Soviet Union, when they still existed, and they are actually able to reduce some of the number of bombs and so on. Huh? Here's another example. Drugs, which you can see now, because now we're in the Winter Olympics. Performance-enhancing drugs for athletes. Okay, so here's a game. The two athletes are competing, and each athlete has a choice. Don't use drugs or use drugs. Okay? Now, if athlete 2 does not use drugs, what does athlete 1 do? You have to look at this column, huh? Then athlete 1 will get better result if they use drugs. So they will use drugs. Okay? If athlete 2 does use drugs, then athlete 1, what do? Well, they have to use drugs also to be in the same position. Otherwise, they have disadvantage. So that means that the dominant strategy here is that both use drugs. But that's worse. You get 2-2. I mean, they may get slightly better results, but in terms of their health, in terms of honesty, in terms of competition, it's worse. Okay? And if they would not use drugs, they would have an honest competition. You have a better payoff. But the rational behavior, where each athlete decides independently, is pointing to this, that both use drugs. Of course, the Olympic Committee knows that this is not a globally optimum solution. So they will try to fight this by installing other mechanisms, like drug testing and so on, so that the payoff for using drugs is worse. Because if you use drugs and you get caught, then you're completely disqualified. So you have another matrix where using drugs actually gives you a chance of being much worse. You get disqualified. It's like minus infinity, okay? You never can win. So they try to modify this, but without the kind of global action of drug testing, each athlete would be using drugs, okay? Of course, they would not say it, but they would be doing it, because that's the rational solution. Okay? So you can figure that out by game theory. Okay, so of course the question is, and I mentioned it a little, how do you avoid the worst solution of rational, selfish decisions? Okay? Or you can change the payoff by taking collaboration into account. So by improving the non-drug using case, for example, by making the price of using drugs, there's maybe a 10% chance of getting caught, but if you do get caught, you're disqualified. So that actually reduces your payoff if you use drugs, and maybe it's not in your benefit anymore. So the percentage, the payoff has to decrease. Okay, so that's one way. Or yeah, you can change also in other ways the rules. For for example, in the exam example, we can change a little bit the rules. Let's say we make the exam easier, which means if you get study, you get 100%. If you don't study, you get 96%. I'm sure you would love exams like that, though. You still get 96 if you don't study. If you have this rule, then you get this payoff matrix. And in this case, the dominant strategy is the best globally, okay? So it all depends on the situation. You see, it's not always obvious. There's many, many possibilities, okay? Okay, so I want to introduce different kinds of games now. I talked about dominant strategies, but let's try to make some definition now. Okay, I want to go to some more sophisticated things. So dominant strategy is very simple, huh? It's when you always have one best move, but in real life it's not going to be like that. So we need to be a little bit more subtle, a little bit smarter. So I have to define a concept called best response. Okay, it's actually very intuitive. Okay, player 1 makes a move, S. Player 2 makes a move, T. And player 1 wins P1, and player 2 wins P2. Okay, so that's the payoff matrix, huh? Player 1 wins P1, and player 2 wins P2. It turns out P1 is a function of S and T, yeah? If you consider this number a function of the two moves, it's the payoff to player 1 as a result of ST. So that ST is actually the moves by both players, huh? And P2 is the payoff to player 2 from ST. Okay? So S for player 1 is a best response to T. So let's say player 2 does T, okay? And player 1 has two choices, S prime or S. Now, if P1 is bigger than P1 prime, then S is the best response. It's the best move. If player 2 does T, player 1 should do S. Okay, so S for player 1 is best response to T. If for all other strategies, the payoff from S is bigger than the payoff from T, or equal. Okay, so that's best. We have strict best response if it's strictly greater. Okay, so the strictly dominant strategy is that the S for player 1 is the same one for all of the choices of player 2. Okay, so it's important to get your thinking in terms of player 2 chooses and player 1 responds. A player does something and a player has a response. Okay, because we're going to reason like that also for the other games. Okay, so S is best response to T. Okay, does a player have one strategy, one move, that is always the best? Well, that one is called strictly dominant. And in Prisoner's Dilemma, we had it. Confessing is always the best. So the best response to MC is C. The best response to C is also C. So C is the best response to both. So it's the dominant strategy. And because it's strictly more, it's the strictly dominant strategy. Okay? So in Prisoner's Dilemma, both players have strictly dominant. And clearly that's what you do. If you have it strictly dominant, you do it, okay? And in the exam or presentation, I'll let you look at that. Okay, that's also very easy. But most times it's not so simple. Okay, maybe the strategy is not strictly dominant. But maybe there's no strictly dominant strategy. In fact, I can easily tell you again, in rock, paper, scissors, there's no strictly dominant. Question?
Je voulais dire que je trouve ça dommage que ça soit une stratégie dominante. En fait, si on prédit le système, alors on sait quelle réponse va être apportée au système, et du coup, on sait voir qu'il y a un point qui est, on s'est compris par rapport à la stratégie dominante, qui est de
Attends, je ne comprends pas ta question. Tu peux le dire plus clairement, enlever le masque peut-être. Take off your mask.
Comme c'est une stratégie dominante, on sait prédire que tout le monde va faire la stratégie.
Absolument. If there's a dominant strategy, then the player 2 knows that player 1 is going to pick it, of course. Right? Absolutely, yes, because it's the rational. Each player is rational. But you'll see, usually there's no dominant strategy. Yeah? It's only a very simple case. Dominant, it's only very simple cases. Because very often there's no dominant strategy, so it's not so easy.
Alors, il sait ce qui va leur arriver. Parce qu'il faut partir du
Bien
principe.
sûr. A player might be completely sure what the other one will do because each player is assumed to be rational. Each player will maximize their payoff. But that's reasonable. Player 2 tries to get the best. And player 1 knows that player 2 tries to get the best. Absolutely, yes.
On part sur le principe que les êtres humains sont la machine est par défaut.
But you'll see, in this, this is a simple case. So let me rephrase in English. So here we're assuming that every player tries to maximize, and each player knows the other one will maximize. So the question is, in real life it might not be like that. That's true. In real life it might not be. But if it's not, then other kinds of reasoning are done. But in the local selfish reasoning default case, this is the most basic default reasoning. Yeah? Of course you can have other reasoning, and we will look at the other reasoning. Okay? But we have to start with the simple reasoning where each player is just trying to maximize. Okay? And we'll see other reasoning later. Huh? So be patient, you'll see. Okay? So here's another game. In this game, one player has a strictly dominant strategy, but the other player does not. Okay? So here's a game with two firms, so companies. They are making products, and they can choose strategy. Either make low price product or upscale product. Okay? So low price product, what could it be? As a car, it could be like De Chevaux or something, and as a upscale, it could be like BMW or Mercedes or something. Or the low price product could be a PC, and this could be a Mac, whatever. So this is a typical situation. Here's a table. So here are the rules we take. We assume there's two kinds of customers. 60% will only buy the low price, and 40% will only buy the upscale. So each of those two have their market. Okay? Of course, you can change the numbers. Huh? Also, firm 1 and firm 2, there's reputations. Firm 1 has a much better reputation than firm 2. So if they compete directly, firm 1 will get 80% of the sale. So what happens? Okay, so here is the payoff matrix coming from these two rules. So for example, if firm 2 does low price and firm 1 does upscale, then the consumers, if they want to buy low price, they only have firm 2 as a possibility, and if they want to buy upscale, they only have firm 1. So firm 1 will get the full set of upscale customers, and firm 2 will get the full set of low price customers. So the payoff is 0.40, 0.60. Okay. Now if both do low price, if both are doing low price, well then they only have 60% of the customers, so they have less customers, and firm 1 will get 80%. So the sum of these two is going to be 60%, and one of them will get 80%, so 4 times as much as the other. So you get 0.48, 0.12. Okay, and you can compute the others in the same way. If they both do upscale, okay, then the total market is only 40%, because 40% by upscale, and again, firm 1 will get 80%, so it's 0.32, 0.08. So you can make the payoff table. Now we can look at the strategies. in order to see what will firm 1 do. Firm 1, we look at the red lines. So if firm 2 does low price, then firm 1 should do low price to get higher. If firm 2 does upscale, firm 1 should also do low price. So firm 2 should always do low price. That is their strictly dominant strategy. But what about firm 2? Okay, firm 2 does not have a dominant strategy. Because if firm 1 picks low price, then firm 2 should do upscale. Now I'm comparing the blues, 40 and 12. Whereas if firm 1 does upscale, then firm 2 should do low price, 60 versus 0.08. So what firm 2 does depends on what firm 1 does. So what can we learn from this? Well, firm 1 is going to be rational. We're assuming it's rational. So they will pick low price. And firm 2 is going to then react to firm 1's strategy. Okay? So basically, what's going to happen then, if everything goes according to these rules, is that firm 1 will get 60% of the market, and firm 2 will get 40%. So the intuition here is because firm 1 has a dominant strategy, they don't care what firm 2 does. That's what it means. Firm 1 is so strong, this 80%, they can basically ignore firm 2. Their strategy, they have a dominant strategy. But firm 2 has to stay away from firm 1, or they will be destroyed, because whatever, by firm 1. So if firm 1 does low price, firm 2 must do upscale. They have to stay away. Okay? So this is an example where only one player has a dominant strategy. Okay? See how it works? But it's also possible that nobody has a dominant strategy. There are no dominant strategies. And then we have to be a little bit more clever. I'm going to now look at cases when there's no dominant strategies. Then the solution to this is called a Nash Equilibrium. So what happens when you have a game and neither player has a strictly dominant strategy? Okay? That means neither player has a simple answer. But what are the players going to do? So one solution is called a Nash Equilibrium. Now this solution was invented to solve this problem, but in fact it models also how people think. So what does it mean? The Nash Equilibrium says that each player's strategy is a best response to the other. That means it's an equilibrium because both are together, okay? That means if player 2 picks something, player 1 has the best response to that. But if player 1 picks that thing, then player 2's best response is what it also picks in that case, okay? So I can do something like this. Let me show you how it works. So here is a hypothetical game, okay, with two strategies, A, B, player 1, player 2. Okay? So let's say player 2 picks B. Okay? And we have here, and A is the best response. So A, best response to B. That means if player 2 picks B, player 1 will not pick B because this will be worse. This will get worse, huh? So this is best. But it also is in the opposite direction. If player 1 picks A, then B is the best response to A. So it's symmetrical. Okay? Which means, basically, now I'm comparing these two numbers. I either compare these two numbers or these two. So in the case player 2 picks B, A's best response, 1's best response is A. In the case player 1 picks A, now I look at these two, and 2's best response is B. That means each player has a best response to the other guy. That means neither of them has any reason to change. If A would change, if 1 would change, it would get worse. If 2 would change, it would get worse. Okay? Neither side has an incentive to deviate. So it's kind of an equilibrium, situation. Each one depends on the other doing the best response. But each one will like that because it gives them a better thing than the alternative. Okay? So that we'll see how this works. It's possible that a game has multiple equilibria. We'll see that too. So it's not so simple, the Nash equilibrium. There might be different Nash equilibrium. So this one might be a Nash equilibrium, so which is basically AB, yeah? But maybe BA is also Nash equilibrium. It depends on the game, okay? And then how do you decide? Well, we'll see about that, okay? We'll see about that. Show you some examples. Okay, so I'm going to make some examples. Let me start here. So here's an example. Now we have 3 choices, okay? We have 2 companies, again, firm 1 and firm 2. So these are very nice guys. I know them very well, firm 1 and firm 2. And firm 1 and firm 2 have clients. Firm 1 can sell the garbage that they make to A, B, or C. And firm 2 can also sell their version of the same garbage to A, B, or C. Okay? So firm 1 can talk to A representative and say, I will sell to you. Or firm 1 can talk to B and say, I will sell to you. So each firm has 3 possible strategies. Talk to A, B, or C. Okay? So here's the payoff table. So A is a big guy. Okay? They need a lot of this product, whatever it is. Okay? 8. B and C are smaller. They only need 2 of the product. If the 2 firms approach the same client, so the client sees the 2 guys arriving, they will buy half from each. But firm 1 is very small, okay? Without firm 2, it gets 0. It's like ridiculously small. But if they both arrive, then somehow, because the big guy's there, they think that firm 1 is also a big guy and they will give it business. Okay? So firm 1 needs firm 2. Okay? So if firm 2 picks something and firm 1 picks a different thing, it gets 0. Okay? So we have this payoff. If firm 2 picks C and firm 1 picks A or B, then firm 1 gets 0. But if they both pick C, they will divide it in half, 1, 1. Okay? And the same for B. And if firm 2 picks A and firm 1 picks B, okay? Then firm 1 will get 0, okay? But A, oh yeah, there's another rule. A is a big guy. A requires both firms together. If only one firm approaches A without the other one, then it's 0 for both. So firm 2, even though they're very big, okay, they can't do A by themselves. Okay, they need firm 1 also. So that gives you this kind of funny payoff matrix. Okay? So this is like, in real life, you get these kind of interesting payoff matrices. Okay? So what do you do in this case? Well, neither firm has a dominant strategy. How can you see that? Well, if firm 2 picks A, then there's no one. Then, for example, firm 1 should also pick A. But if firm 2 picks B, then firm 1 should also pick B. So it's not the same. Dominant would mean it would be the same, independent of all the choices here. So neither firm has dominant strategy here, huh? So what do we do? Well, let's take a look now. Firm 1 A is strict best response to A. They have best responses, which means if firm 2 does something, A can respond. If firm 2 does A, then firm 1 does A. If firm 2 does B, then firm 1 does B. If firm 2 does C, then firm 1 does C. Okay, and in the opposite direction, if firm 1 does A, then firm 2 does A. If firm 1 does B, now we're looking at the horizontal lines, then firm 2 does B, and if firm 1 does C, then firm 2 does B. Okay. So that's those are the responses, okay? Now we can actually figure out that there's a Nash equilibrium here, okay? Strategies can be best responses to each other, okay? So the Nash equilibrium, lets me define it. So this was proposed by a mathematician called John Nash, okay, in 1950, and he did many things in economics. And he got the Nobel Prize in 1994. So he was a smart guy. He actually proved that there are always Nash equilibria, even in very complicated games. Okay? Let's say player 1 moves S, player 2 moves T. So the total strategies are ST. This is a Nash equilibrium if S is best response to T and T is best response to S. That means player 1 will not choose something different because it will be worse. And player 2 also will not choose something different because it will be worse. They're best responses. Okay? So this is not a rational play. So now we're getting ahead of this rationality. So the comment that each player tries to be selfish by themselves, now that doesn't work anymore. There's no dominant strategy. So the player has to think about the other player. So somehow they are being rational together, 1 and 2, okay? It's an equilibrium. Equilibrium means there's like a balance between two opposing sides. And each player has no reason to change because it would be worse, okay? If it's the best response, then any other response would be worse. So each player believes that the other will be one part of the Nash equilibrium, then they have an incentive to be the other part of the Nash equilibrium. Okay, so there's actually an incentive for both players to choose the Nash equilibrium. So this is going beyond the simple maximizing thing. Huh? Now we have an incentive. Okay, and let me just go to this example again now. In our two firms example, you can see that AA is actually a Nash equilibrium. That means if A is the best response to A, that means if firm 2 chooses A, the best response of 1 is A. If firm 1 chooses A, the best response of 2, now I'm looking at the row, 4, 2, 2, is also A. So AA is mutual best response. Okay? So that's a Nash equilibrium. And you can show that in this case it's the only Nash equilibrium. How can you show that? Well, just check each of the other ones to see whether it's a best response. So you can do that as an exercise. Huh? This is the only one. Sometimes you have more than one. Huh? That means if the firms are in the real world, they will tend to do this because that's a stable situation for them. That means if they live in this situation, if each one plays by the rules of Nash equilibrium, then each one will get a reasonable result and cannot get better by changing. It's like a hill, it's like a local hill, and they're somehow on the top of the hill. Huh? Firm 1, if it changes, it only gets worse. Firm 2, if it changes here, 4, 2, 2, it only gets worse. Okay? So this is already one step beyond the simple rational play. Okay? So simple rational play with dominant strategy, but if you don't have that, then you go for Nash equilibrium. Okay? Of course, real life is not so simple as this even. Now we're only getting started here. So we can have more than one. So let me now make a break, and then I'll introduce some more games, and they get more and more realistic. As they get more realistic, things get more interesting and a little bit more subtle. Okay, I'm going to ask you a small question just to make it something very clear. So here's our example from before. Okay. So, for example, let's say firm 1 chooses B. Okay? Firm 1 chooses B. So what is the best response of firm 2 to this? You tell me. Firm 1 chooses B. What is the best response of firm 2?
C.
C. Okay. So that gives me 0, 2. But 0, 2 is not a Nash equilibrium. Why not? C is the best response to B, yeah? But this is not a Nash equilibrium. Why not? Why not? I'm inspired by a question asked me by a guy during the break. Huh? It's good, very good question. So C is the best response to B, gives me here. But this is not a Nash equilibrium. Why not? Why not? Yeah?
Because it doesn't maximize the payoffs of both players.
Both. It has to go the other direction too. So C is the best response to B, but B is not the best response to C. If firm 2 chooses C, what is the best response of firm 1? Now I'm saying in the other direction. If firm 2 chooses C, what is the best response of firm 1? C, huh? You look at the column, 0, 0, 1. Not B, okay? So C is the best response to B because we're looking at, this one chooses B, I'm looking at 0, 1, 2. The second part here in the row. Whereas the best response to C is the best response to B, but B is not the best response to C. C is the best response to C. So firm 2 chooses C. Then now I'm looking at the columns 0, 0, 1. The best response is C. So it's not going both ways, you see? So it's not Nash. The Nash equilibrium has to go both ways. And there's only one here where it goes both ways, which is AA. So you can always do best response in one direction, but it has to go both ways. That means both players have to have an advantage of doing the Nash. Huh? The advantage has to go both ways, you see? You see why Nash is interesting, huh? And I made a little diagram here. We saw in the very first game, like prisoner dilemma, you have dominant strategy. So each player is being selfish. And this is the rational play, huh? But one player is being selfish. Whereas in a Nash equilibrium, it's not just one player. They both have to follow this rule, huh? They both have to do the best response to each other. So in some sense, they're collaborating to make a Nash equilibrium because it's in both of their interests. So the selfishness is now going to both players. Okay, you see? So neither of the players has a dominant strategy, so that they cannot just be selfish by themselves, but if they kind of work together a little bit by making a Nash equilibrium, it's a little bit less selfish, but still, they're still being selfish. Right? It's only the two players. They're not interested about society. Huh? And so the Nash equilibrium is actually the two players kind of collaborating. Okay? So it's already a step up from the very simple dominant strategy. Yeah? Okay. But now let's take a little look at some more games. Now I want to look at games. These are called coordination games. or this other kind called anti-coordination games. So there are some games where you have more than one Nash equilibrium. So then the point is, which one do you pick? Because both players, it only works if they pick the same Nash equilibrium. How to choose between them? And I'm going to look at two kinds of games, coordination and anti-coordination. So some of these are also very famous games that a lot of discussion. So here's a simple coordination game, okay? It's called coordination because the goal somehow is that they collaborate. So you and a partner are working together, working on slides for a presentation, and you have a choice. You either use PowerPoint or Keynote, okay? And the other one also chooses PowerPoint or Keynote. And both of them are working at home, making slides, and they decide independently, okay? You can't reach your partner. You have to start working now. You have to decide whether to use PowerPoint or Keynote. So this is a coordination game. Coordination means that the two partners somehow have to coordinate. That's like the best thing. So this is very important in real life, okay? Two manufacturers who are building parts, will they use metric units, the very nice metric units, or the completely bogus English imperial units? I'm extremely objective. So they choose here. If one of them is American, actually this game has been already won. The most manufacturers are in the world, even in the United States or in the UK, have now decided on metric units, okay? English units are only used for the common people, but not for manufacturing. Or two platoons in the army, either they attack on the left or the right. They have to decide, they have to coordinate. People finding each other in a crowded store. Do you start looking on the north part of the store or the south part? Well, if you choose differently, you won't find each other, okay? Either choice is fine. Both choices must be the same. So here's the payoff. If both partners pick PowerPoint, then everything's good, because you can merge the slides, 1-1. Okay, everybody benefits. If both pick Keynote, it's good. But if one picks PowerPoint, the other one picks Keynote, then there's no advantage, okay? You have to redo the work, or things get messy, okay? Okay, so this game has two Nash equilibria. There's two possible stable outcomes. PowerPoint, PowerPoint, and Keynote, Keynote. How can you see that? Well, if I pick PowerPoint, the best choice of the partner is PowerPoint. But if my partner picks PowerPoint, the best choice for me is also PowerPoint. So it works both ways, the best. And the same for Keynote, symmetric. So there's two stable solutions, in a sense. So which one do you pick? So this now already shows the limit of Nash equilibrium. We need something new here. You need something that's outside of this environment, because this is completely symmetric, to let you choose. And this is something called a focal point. There has to be some reason for focusing on one of the Nash over the other, because otherwise they're both equally valid. Okay? Here's another example. Two drivers are approaching each other at night on an undivided country road, very narrow country road. Okay? Now, they're like this. So they should try to avoid each other. You understand that? They don't want. So should each driver move to the right, to their right, or to the left? If one moves to their left and the other moves to the right, they crash. Okay? And inversely. So basically, either each one moves to the right or each one moves to the left. So both solutions are good and both are Nash equilibrium. But which one you pick? So there's actually a social convention here. In continental Europe, normally cars will move always to the right part of the road, whereas in the United Kingdom, they always move to the left part of the road. So if you're driving in the United Kingdom, you should probably move to the left. If you're in Belgium, you should probably move to the right, okay? And we're extremely lucky that those guys are living on an island. Huh? So you can see that this is exactly the same situation. There's two Nash equilibria. So you can see it really works in many cases. Huh? This is game theory stuff. Huh? Many different situations. Huh? Okay. So here's another version of this. Okay. Now, suppose that each player, it's a similar game, power and point keynote, but each player prefers keynote. Okay, for some weird reason, I have no idea why they would do that, but yeah, they prefer keynote. The alternatives are equal. So there are still two Nash equilibria, 1, 1, and 2, 2. So, but one of them gives higher payoffs to both players. Okay? So, using this focal point idea, you have to disambiguate somehow, make a difference between these two Nash equilibria. So you can, for example, predict that you want to use an equilibrium that gives you higher payoff. So 2, 2 is higher for both players. So there's a very reasonable that 2, 2 will be a more likely Nash equilibrium. Okay? So again, you have to break the symmetry in a sense. So you have to pick one of them. Okay? But things can get even worse than this. You can maybe imagine how it can get worse. So here it gets worse. Now we have 1, 2, and 2, 1. Again, there's a preference to one to the other, but the players don't agree. So again, there's two Nash equilibria, 1, 2, and 2, 1. But you would prefer to use PowerPoint, whereas the partner would prefer to use Keynote. Sorry, the partner, yeah, so the partner likes Keynote and you like PowerPoint. Huh? So there's still two Nash equilibria. No, sorry, I'm confused. I like Keynote, but it gives me a higher payoff, but the partner likes it less, so only gets one out of it. Whereas if the partner picks PowerPoint, they get 2, and I only get 1 because I like PowerPoint less. Okay. So it's like that, huh? So there's two Nash equilibria, but each one favors another player, so it's completely symmetric. This is a very famous problem called Battle of the Sexes. Okay, husband and wife want to see a movie together. They can choose a romantic comedy or an action movie. So, of course, the husband, he loves romantic comedies, and the wife prefers Fast and Furious or something, action movie. But here you can either do power romance, and one of them is very happy, and the other one is less happy, or you can do action, and one of them is less happy, and more happy. So you can't make both of them equally happy, okay? So so what do you do? Again, you have to find something that's outside of the game, okay? And there's even another variation of this. You can see that even so simple games, and even in the real world, you can see these situations happening. This one is a famous one too, called Stag Hunt. Chasse au cerf, French, huh? Stag Hunt. So you have two hunters. They either want to hunt a stag or a hare, a lièvre, huh? Which is kind of a big rabbit, huh? So, okay, they go hunting. This is actually famous. It's very old. It actually comes from some total weird philosopher called Jean-Jacques Rousseau. Maybe you heard of this guy. He's extremely obscure. Most people have forgotten. But still, this guy has explained this. Two hunters in a forest. If they work together, they can catch a stag, which is a big beast. So yes, they're very happy they get 4-4. Okay? On their own, they can each catch a hare. Hare is a smaller animal. Hunter 1 can hunt the hare, but if Hunter 2 tries to hunt the stag and Hunter 1 tries to hunt the hare, then Hunter 1 will get the hare, but Hunter 2 will get nothing. Okay? And if they both hunt hares, they will both get a hare. You get 3-3, okay? So you can see this one is also a little bit like, slight variation of prisoner's dilemma in a sense, huh? But different, okay? It's different because there's no dominant strategy anymore. In prisoner's dilemma, there was dominant strategy. Here it's not. Here you have two Nash equilibria. Stag, stag, and hare, hare. Okay? If hunter 1 hunts a stag, then the best for hunter 2 is also stag. If hunter 1 hunts a hare, okay, then the best for 2 is also the hare. So stag, stag, and hare, hare are two Nash equilibria. So what do you do? Well, maybe stag, stag is better, but it's also, yeah, more work or something. Huh? So again, this is similar to prisoner's dilemma. But now there's two Nash equilibria, and if they try to cooperate, but the other one does not, then there's punishment. Okay. Now the exam or presentation game, which we introduced in the beginning, can be tweaked. You can turn it into a Stag Hunt, okay, like this. If you change a little bit the rules, both get 100 on the presentation. At most one, they both get 84, okay? So that means you need really both to work on the presentation. Then you get this, and then you get this Stag Hunt notion, where one of them can get, where the hunting the hare, if I do hunt hare, I will never lose anything, okay? It's always the same. Whereas the other guy will lose. If hunter 2 picks hunt hare, they will always get the hare. Okay? So it's kind of the safe solution, you see? If I pick hunt hare, I'm safe because I will always get a hare. But if I pick hunt stag, and the other guy picks hunt hare, then I can get 0. Okay? So there's like a safe solution here. So it's not the same as prisoner's dilemma. Okay, so that's even another variation, the coordination. So the best thing here again is that they coordinate. Okay. Now there's more variations. There's the opposite kind, which is called anti-coordination. Here's another one. This is a famous one too. This one is called the hawk-dove game. Les pigeons et les faucons, or something like that in French. So, two animals have a contest how to divide a piece of food. And the animal can either be aggressive, fight for the food, or be very passive. Okay? Now, if they both are passive and they're very nice, they divide the food in half. So the 6 turns into 3-3. Okay? If one is aggressive, it gets most 5-1. Okay? So, but if both of them are aggressive, then the food is destroyed, or someone steals it or something. A third animal sees the two fighting and picks the food. This is a famous fable also, La Fontaine. So this again, you can model it in terms of game theory. It's nice, huh? So you get some interesting situation here. So what do? Do you be aggressive or passive? What's the solution? Of course, the best, it depends. If you know the other person is a milk toast, or how do you say, a minable, you can be aggressive, and maybe you're not sure. So there's two Nash equilibria here. Dove-hawk and hawk-dove. So if I pick dove, the best response is hawk. Okay. If I pick hawk, now I'm looking horizontally, the best response to hawk is dove. So hawk-dove is a Nash equilibrium, and dove-hawk also. So these are the two equilibria, actually. So the equilibrium is when both of them are different. And, okay. This is the one where they actually both, so the real passive one will still get a little bit, not nothing, and the aggressive one will get more. It's funny, huh? The best solution is not 3-3 here. And the reason is that the amount of food here is constant. It's one of the reasons for this. So still there's no unique solution. So two countries, they choose whether to be aggressive or passive. And so this is something that you can see every day now in the news. Okay? So there's one country who's choosing the aggressive. I'm mentioning no names. Hi Vlad, how are you? So one of them is deciding to be aggressive, but maybe not all. But if they're both aggressive, then everybody loses. Okay? So the aggressive one is looking at the other one and saying, I expect the other one to be dove, but he's not being dove. And so we're both aggressive, so I lose. So maybe I should be less aggressive, then I can be the dove, he can be aggressive, so I won't lose. Okay? So you could actually see that the aggressive one in the last 2 days is starting to be slightly less aggressive. Maybe he did not expect, maybe he expected more of a dove-like response. So you can look at this situation in terms of game theory. And you can predict one will be aggressive and one will be passive if you are following Nash equilibrium. But you don't know which one, of course. That depends on external situations. Okay? So again, our famous examiner presentation, you can make a hawk-dove version of that by tweaking a little bit. You can see that real life can go through all of these possibilities. It really depends on the rules and the payoffs. So the original one was like prisoner's dilemma. Okay, with a small change, it was like Stag Hunt. Okay, no strictly dominant strategy. Coordination is rewarded, miscoordination is punished. With another small change, it can be like hawk-dove. Hawk-dove means one person should do the presentation and the other one should do the exam, and that gives the best result. Okay? Okay? So if you change the rule a little bit, for example, if neither prepares for the exam, or sorry, the presentation, you get a very low rate of 60. And that gives us something like this. Okay? So if nobody prepares for the presentation, you get some very bad result. Everybody's losing here. So now this is looking kind of like hawk-dove. The best solutions are here. So depending on small changes in the points, things can be very different. You see, it's not so, real life is actually very complex. You can model many things as games and figure out rationally what is the best solution, but small changes in the numbers can change completely the strategy, okay? Best strategy. It's interesting, huh? So it's actually a good example to try to apply this in real life. Okay. Okay, so still we're not done. Things get even more interesting because sometimes you can't just pick one or the other choice. Sometimes you need to randomize. This is called mixed strategy. Okay. Again, this is really similar to what happens in the real world. Okay? Now, in the previous sections, we had games with more than one Nash equilibrium. You can also have games with 0 Nash equilibria. But actually, that's only 0 if you have to pick one strategy or the other. If you are allowed to randomly choose between, like 50% A and 50% B, if you're allowed to do randomness, then you always have Nash equilibria. Okay? So the previous case, you can have no Nash equilibria if you were only allowed to pick one strategy. But if you were allowed to randomize, then you always have Nash equilibria, and that's also interesting in the real world. Like a penalty kick, for example. If I kick, do I kick to the right or the left of the goal? The defender, the keeper, does the keeper jump to the left or the right? And if so, that's a game. You can model that in game theory. Yeah? So if you have what's called attack-defense games, mixed strategies can actually be very useful. Okay. let's say one player attacks and another one defends. Now the attacking one has two strategies for attacking. The defender has two defenses, defend against A or defend against B. Do Hitler's forces go into, there was two possible choices. There was Normandy and there was the other one, forget. There was two possible shores that could come in. And where do you defend? Where do you attack? Okay. If the defender defends against the same attack, then the defender basically wins. The defense is good. Defender gets the payoff. But if the defender defends against the wrong attack, the attacker gets a good payoff. So for example, in the penalty kick, if I kick to this side, the keeper jumps to the same side, then the keeper will usually get the ball, okay? And I will not get the goal. So this is an interesting kind of a game that happens a lot, okay? So to show this idea, let me make a very, very simple game. It's very psychological, called matching pennies. Small coins with heads and tails. Pile de face, heads and tails. Two people hold a penny, and then they show heads or tails. If they match, player one loses the penny. If they don't match, player one wins a penny. Okay? So it's like this. Heads, heads, player one loses, and player two wins. Heads, tails, player one wins, player two loses. This is a very interesting kind of game because this is called a zero-sum game, which means that the payoffs always sum to zero. There's no net gain or loss. It's like the total amount of money is conserved, okay? The total profit is conserved. Zero-sum, okay? So many attack games, defense games are like this. Here's the Allied landing. It's either Normandy or Calais, okay? So you either land at Normandy or Calais, and the German army defends Normandy or Calais. And of course, we know that the German army made the wrong choice, okay? And it's because the Allied army was very smart, and they did all kinds of decoy to pretend they were going into, it was Calais, and then they went into Normandy, And the German army was fooled. They each tried to be smarter than the other, okay? So this is an example, okay? So so how do you play this game? That's the question now. How do you play matching pennies? What's the best way to play this? Okay? So there's no best responses to each other. So there's no Nash Equilibrium if you pick one strategy, okay? Because you can always pick the other one and it's flipped around, okay? So if player two picks heads, then player one picks tails. But if player one picks tails, then player two tails here. Player two will also pick tails, okay? So there's no pair, there's no Nash equilibrium. So what do you do? The solution here is to randomize, that you don't always pick one or the other, but you make an unpredictable choice between heads and tails, okay? So now we're going to introduce randomized behavior. And this is called mixed strategy. And the idea is the following. So I will not pick heads or tails, but I will choose a probability for picking heads or tails. So if I can pick a real number between 0 and 1. So my strategy is not heads or tails. My strategy is a number between 0 and 1. And it says, if it's, for example, 0.25, it means I will pick heads with probability 0.25, and tails with 1 minus 0.25. So the number tells me what is the probability of picking heads. Okay? And the strategy for player 2 is also a real number. So now player 1 picks a number, player 2 picks another probability, and the two probabilities are fighting One is the best, okay? Now the game is already different, okay? There's not just 2 possible moves in this game. There's actually an infinite possible moves, okay? Each number is a different strategy, okay? And so how do we solve that? So it's very interesting. We say pure strategy when it's 0 or 1. So before we always did exactly heads or exactly tails. So this is more general, huh? You can also do that 0, 1, but you can do now random. So how do you pick P or Q? Okay. Okay. So let's look at it. The payoffs also will be some random numbers. Huh? There's some expected values. Huh? So we need some approach, principled way. Okay. Okay. So let's take a look. Again, let's see how a player reacts to another player. So let's take a look at player 1. If player 2 chooses Q, it means heads with probability Q and tails with probability 1 when it's Q. If player 1 then chooses strategy H, then player 1 will lose 1 probability Q and gain 1 minus Q. So the expected playoff of player 1 by choosing H is minus Q plus 1 minus Q. So it's 1 minus 2Q. Okay, so this is expected on average. Huh? It's not something, it's if you have many instances of the game. Okay, so if player 1 plays H, it's this number. Huh? It's minus Q plus 1 minus Q is 1 minus 2Q. But if player 1 plays T, the expected playoff is 2Q minus 1. Okay, so you either have 1 minus 2Q or 2Q minus 1. But of course you don't know the value of Q. You don't know the value of Q. So what do you do now in this? Okay. Okay. Okay, we may have to make another assumption here. Each player will somehow try to maximize their expected winnings, because you can't just do that for one single game. It doesn't work. Huh? So here's the mixed strategy version. The strategies are probabilities of playing H. The payoffs are the expectations from the 4 pure outcomes. Okay, so here's one possibility. Is there a Nash equilibrium now for this version of the game? Actually, no pure strategy. Both sides have to be mixed. No pure strategy can be part of a Nash equilibrium. Suppose that a pure strategy, that means either H or T, will be part of an equilibrium, then player 2's unique best response is also pure. But that doesn't work. We know that, because we know there's no pure Nash equilibrium. Okay? So the best response has to be also something mixed. Okay? So how do we figure it out? So here's one way of doing it. So this is not so simple to think about. So assume player 2 uses strategy Q. If player 1 would do H, then they would get 1 minus 2Q. If player 1 would do T, they would get 2Q minus 1. So here's the subtle idea. If these two numbers are different, that means one of these two actually gives a higher expected payoff, and it would be the best response. If one of these two numbers is bigger than the other, then the best response of player 1 would be that one, because it would give the higher payoff. Okay? But we know this can't be a Nash equilibrium. We know it doesn't work. Okay? So the only solution, actually, is that it's neither the other one. That those two have to be the same. That these two have to be the same. that player 2 has to make it so that neither H or T is the best strategy. So the only way to make that work is if these two were the same. Okay? So if we have a Nash equilibrium, it can't be pure, and that means these two numbers have to be the same. One of them is not allowed to be higher. That means Q has to be equal. If you solve this, it turns 4Q equals 2. Q has to be a half. And by symmetry, also P is a half. So the Nash equilibrium for this game is 1/2, 1/2. That means player 1 picks heads 50% of the time, and player 2 picks heads 50% of the time. And each of those is a best response to the other. Okay? So this is something you can verify. I leave it as an exercise, but I will give you the answer next week in the course. Okay? So think about it. Each one is a best response to the other. This gives there's actually a general principle. This is actually very intuitive. This is called the indifference principle. If player 1 believes that player 2 will play H more than half the time, then player 1, of course, should play T to get some advantage. Okay? So if there's any bias towards H or T, then the other player should take advantage of the bias. Huh? If player 2 is playing lots of H's, then it's clear player 1 should play lots of T's to get some advantage. Okay? But if player 2 makes them equal, H or T, then there's no advantage on player 1 to picking H or T. So player 1 is indifferent. Player 1 cannot exploit player 2. Player 1 cannot take advantage. Player 2 is unpredictable, does not give any advantage. So this is actually a general principle that we can use. You have to randomize your choices so that neither of your choices will give an advantage to the other guy. They have to give the same thing. Okay? This is a general thing. And with that, we can actually solve a lot of these games. Okay? So let me give just two examples. So here's first some intuition. In sports, this is actually used a lot. Players will actively randomize. In tennis, for example, when you serve, you can serve right up the middle, or you can serve to a corner. And if you're a very good pro player, then the other guy, if he makes the wrong guess, will probably not be able to return your serve. Okay? So there's a randomization. Serve up the center or to a corner, or the penalty kick to left or right, or bluffing or not bluffing. In poker, it's not deterministic. There's randomness. Of course, rock, paper, scissors, randomness. Okay? So actively randomizing. It actually also works in a population. Okay? If I have a group of animals, some of them can be aggressive, some of them can be passive, and the proportion of the aggressive and passive ones is also kind of mixed strategy. Yeah? This is actually something doing with biology. Chess chapter 7. We will not look at that. I'm just mentioning it. Let me show you now American football example and European football or soccer example. So I don't know if you understand the rules of American football. Maybe not. So I have to explain a little bit. So I kind of understand this because I lived for some years in the US and I saw a lot of those games. Okay. So you have two teams and they're on this field. Okay. And they're opposing each other and going from one side to the other. They're at one position in the field. And one team has the ball and it tries to go that way. And there's two ways it can go that way. It can give the ball to somebody and that person runs until a whole bunch of guys jump on him and push him down, okay? Or he can pass the ball, but that's dangerous because maybe someone from the other team captures it. And if someone from my team captures it, I can make a lot of gain, okay? So there's two offenses, there's two attacks. I either pass or I can run. If I pass, then the gain can be a lot because I'm throwing the ball. And if the defense has a choice, I either defend on a pass or defend on a run. So defending on a run means I basically put a guy in front of every guy on the other side, and they're pushing each other so they can't run, okay? Defending a pass means I'm running back, and I'm seeing if anyone is running and going to that guy so we can't catch them, okay? So defending pass or defending run. So if I pass, and they defend on pass, nobody gains anything. And the two stay in the same place, okay? So a lot of this game is, you do that, and then it's called downs. First down, second down, and they're always at the same place. But maybe there's a gain, okay? If this one does a pass and the other defends the run, then the pass will work and he gains 10 yards, okay? This is very nice, or more, okay? Or if he does a run and the other defends for the pass, then they will actually be able to run 5 yards and gain. Okay? So what is the best strategy for this? So there's no pure Nash equilibrium here. There's no dominant strategy here. Okay? You understand the rules, what I explained to you? You see how it works, huh? I pass or I run. And the other one defends on pass or run. Huh? Okay, so how do you figure it out? Well, you use the principle of indifference, and you can figure out how you can play this game best. Okay? So there's no Nash equilibrium. Let's make some computations now. P is the probability of doing a pass, and Q is the probability of defending against a pass. And let's use the principle of indifference. That means the offense has to choose the probability so that the gain is the same, that there is no advantage. Because if there's a different gain, then the other side can take advantage of it. Huh? Okay. Okay. So this one defends against the pass with probability Q. If the offense passes, the gain is 0 times Q plus 10 times 1 minus Q. Okay, 10 minus 10Q. If the offense runs, the gain is 5Q, because 5, this is the probability of defending a pass. So you gain 5, and 0, 1 minus 5Q. These two have to be the same. These are the two payoffs. If they're different, then the defense can take advantage of that. If these two numbers are different, the defense can pick the higher one. But you want to minimize that, so they have to be equal. So the indifference principle says they have to be the same. The gains from these two. And if you compute that, it means Q is equal to 2/3. That means the probability of defending against the pass is 2/3. You can also compute the probability of passing. If you do that, you get 1/3. That's kind of funny, isn't it? Pass is very powerful. If you win, you get 10 gain. But you only use your powerful move 1/3 of the time. 2/3 of the time you're going to use your weak move, which is run. And that's the best. Okay? It's interesting. I think that's an interesting result. So you can actually rethink about it. Passing is the offense's most powerful weapon because they get 10 yards gain. But you only use it 1/3 of the time. Why not? Why don't you use your more powerful option more often? Because you can actually understand why if you see the calculation. If you would do that, the defense's best option would be to always defend against the pass, and you would not gain anything, okay? And you would actually do worse if you do the computation, okay? If the two numbers are not the same, then the defense always picks the higher one. Huh? Always. They would have a pure defense. Okay? Well, let's say instead of 1/3, just try 1/2. Well, even that you can see is not as good. The offense will actually get payoff if you do that. They will always defend against the pass. Okay? So you will actually have less payoff if you do that. So another way of thinking, the defense will defend against the pass 2/3 of the time, most of the time, even though the offense only uses it 1/3 of the time. And that's because the pass is so powerful. You have to defend, and if you do that, then you have neutralized the power of the pass, in a sense. Huh? You see, that's interesting, right? Isn't it neat? So you can actually understand strategy in a real live game. Okay? So let me stop here. Next week we look at more things like penalty kick and more games. Okay? But let me stop here for now.